thereafter we developed techniques to compute eigenvalues by looking into the notion of a characteristic polynomial of a matrix, and then we proved that it is invariant under similarity, and therefore we could talk about characteristic polynomials of a linear operator as well. We also noted that if a linear operator or a matrix is diagonalizable, then the characteristic polynomial, the corresponding characteristic polynomial splits. In this week, we begin by discussing the notion of diagonalizability a bit further. So, we would like to ask the converse to this last statement we made, namely that if a linear operator is diagonalizable, the characteristic polynomial splits. We would like to ask, if the characteristic polynomial splits, can we say anything about the diagonalizability of the linear operator? So, we begin by recalling just quickly the notion of diagonalizability and observing that the linear independence of the eigenvectors is an important notion to study. So, let us begin by, so let us recall that a linear operator T on a vector space V say of dimension n. So, we will focus our attention all through to finite dimensional vector spaces in this video. So, recall that a linear operator is diagonalizable if there exists a basis consisting of eigenvectors. There exists a basis consisting of eigenvectors of T, or a linear matrix A is diagonalizable if there exists a basis of eigenvectors in Rn. So, in particular, if say V1, V2 up to Vn are n linearly independent eigenvectors, I just wrote IND for independent. So, if we take n linearly independent eigenvectors, any linearly independent set of size n should necessarily be a basis in a vector space of dimension n, and hence this will turn out to be a basis. So, if these are eigenvectors of T, then we have a basis of V consisting of eigenvectors of T, and hence T is diagonalizable. Right. So, this suggests that studying when the eigenvectors of a given linear operator are linearly independent is of importance. So, let us try to get hold of a condition when we can say this. So, that is captured in this theorem. So, suppose T is a, so let T be a linear operator on a finite dimensional vector space V, say of dimension n. Suppose we have k distinct eigenvalues of T. So, if lambda 1 to lambda k are distinct eigenvalues of T, and suppose V1 to Vk are eigenvectors of T corresponding to lambda 1 to lambda. So, let me write it like this. Suppose Vi is an eigenvector of T corresponding to lambda I for each I. Then V1, V2 up to Vk are linearly independent. So, the eigenvectors corresponding to distinct eigenvalues should necessarily be linearly independent. So, the proof. Let us consider a linear combination of Vi's which are equal to 0. So, let A1 to Ak be such that A1 V1 plus A2 V2 plus Ak Vk is equal to the 0 vector in capital V. So, we would like to show that each of the Ai's are 0. That would establish that V1 to Vk are linearly independent. So, to do that, let us observe a few things. So, the first observation is that if you look at T minus lambda Ki acting on any of the Vj's, notice that this is just going to be equal to Tvj minus lambda Ki Vj, which is, let me write it down directly, lambda j minus lambda k times Vj. So, therefore, apply maybe not, let me not give names, apply T minus lambda Ki to the equation A1 V1 plus A2 V2 or to the vector A1 V1 A2 V2 plus up to AK Vk. That will be the 0 vector because T, any linear operator takes 0 to 0. So, T minus lambda Ki on A1 V1 plus AK Vk is equal to T minus lambda Ki acting on 0, the 0 vector, and this should necessarily be the 0 vector. Any linear operator maps the 0 vector to the 0 vector, 0 belongs to the null space, right. Right. So, this however manifests as the following. This implies lambda 1 minus lambda k times A1 times this into V1 plus up to Ak minus 1 into lambda k minus 1 minus lambda k times Vk minus 1 is equal to 0. When acted on Vk, T minus lambda Ki will kill Vk because Vk belongs to the null space of T minus lambda Ki. Therefore, this is what we finally get. Let us do the same trick. Consider T minus lambda K minus 1 I acting on Vj. This is equal to lambda j minus lambda K minus 1 times Vj. So, by a similar argument as above, we have A1 times lambda 1 minus lambda k, lambda 1 minus lambda k minus 1 times V1 plus up to Ak minus 2 lambda k minus lambda k minus 2 minus lambda k into lambda k minus 2 minus lambda k minus 1 Vk minus 1 is equal to the 0 vector. Now, keep applying T minus lambda k minus 2I, lambda k minus 3I and so on after k minus 1 such steps. We have A1 times lambda 1 minus lambda k, lambda 1 minus lambda k minus 1 up to lambda 1 minus lambda 2 times V1 is equal to 0. But notice that lambda j's are all distinct. So, lambda 1 minus lambda j is not equal to 0 for j not equal to I. So, the term in this big bracket which I just drew cannot be 0, and V1 is given to be a non-zero vector. This implies that A1 is equal to 0. Since lambda 1 minus lambda k dot 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 times lambda 1 minus lambda 2 is not equal to 0. Similarly, so hence what do we have? A1 is equal to 0 implies A2V2 plus AKVK is equal to the 0 vector, right, because A1 has already been proved to be 0. By a similar argument, we can conclude that A2 is 0. A2 is equal to 0 and so on. So, therefore, V1 to Vn, if they have a linear combination equal to 0, the coefficient should necessarily be 0, and therefore, V1 to Vk are linearly independent. So, proved the result. All right. So, this is a powerful result in the sense that if we have a matrix which has n distinct eigenvalues, then it is necessarily diagonalizable. So, let me just write it down. So, corollary, if an n cross n matrix or a linear operator T on a vector space V which has dimension n, if an n cross n matrix A has n distinct eigenvalues, then A is diagonalizable. So, that is a statement which we can say about linear operators on T, linear operators T on V, where V has dimension n, and if T has n distinct eigenvalues, then T is diagonalizable. So, let us look at an example. So, consider this matrix A to be 1 minus 2 1 4. This is certainly not a diagonal matrix. We could get hold of the eigenvalues and maybe get hold of the eigenvectors, but let us just look at the characteristic polynomial and see what the eigenvalues are. Yes, let us not. So, the characteristic polynomial f of lambda polynomial of A is given by this is equal to lambda 1 minus lambda into 1 4 minus lambda plus 2, which is equal to lambda square minus 5 lambda plus 6, which is equal to lambda minus 2 into lambda minus 3. So, the roots of the characteristic polynomial are 2 and 3 respectively. This is a 2 cross 2 matrix and we have 2 distinct eigenvalues. So, yes, this is a diagonalizable matrix. We do not have to really explicitly get hold of eigenvectors and check for that, but yes, it is certainly the case that the eigenvalues are distinct and hence n equal to 2, each of the eigenvalues will be a basis or rather linearly independent by this argument. So, linear independence follows and therefore, it will be a basis by the observation prior to that. Okay. So, let us look at diagonalizability in greater detail. So, of course, we got hold of one condition when we can say that a given linear operator is diagonalizable, namely that if we have distinct eigenvalues, n distinct eigenvalues of an n cross n matrix. But that is many times not going to happen, and we would still like to say or we would like to still ask the question whether even in the scenario when our eigenvalues are not necessarily n distinct of them, can we diagonalize our given linear operator. So, let us look at more examples to consider this particular problem. So, let us look at this example of say A being equal to say 2 0 and 0 2. What will be the characteristic polynomial here? The character, this is already a diagonal matrix, as you can see. The characteristic polynomial without too much effort, we can say that of A is lambda minus 2 the whole square. As you can see, the eigenvalues of A, or rather the eigenvalue of A is just 2. It is a 2 cross 2 matrix. It is a linear operator on a vector space on dimension 2, and we only have one eigenvalue. So, we cannot certainly use the previous example or rather previous theorem to conclude that this is diagonalizable, but we know for a fact that A is diagonalizable because it is already a diagonal matrix. So, it is indeed possible that the eigenvalues are not distinct, and we would like to ask the question of whether our linear operator is diagonalizable. So, we would be naturally led to conjecture that yes, if it splits, maybe the matrix is diagonalizable. So, that could be the next guess that we can have, because diagonalizability certainly forces the characteristic polynomial to split. So, if can we say that if the characteristic polynomial splits, our matrix is diagonalizable or our linear transformation is diagonalizable. So, to answer that question, let me give you another example by slightly tweaking this. So, let me call it example 1. Let us look at example 2, where A is equal to 2 1 0 2. This is just a slight modification from the previous case. And what would be the characteristic polynomial here? The characteristic polynomial of A is given by, again it will be the same one as above. It's an upper triangular matrix. You should go back and check that this is just lambda minus 2 the whole square. So, we are in the setup where the characteristic polynomial is exactly the same as the characteristic polynomial as in example 1, and in the example 1 our matrix was a diagonal matrix, right. So, f of lambda is equal to lambda minus 2 the whole square implies that the eigenvalues of our matrix A is just 2. So, because they are the roots of the characteristic polynomial, right, the eigenvalues. Hence, 2 is the only eigenvalue, 2 is the only eigenvalue of A, as in the previous case. Now, let us try to, so this matrix is certainly A, as you can see 2 1 0 2, 2 1 and 0 2. This is certainly not a diagonal matrix to begin with. So, let us see if it is diagonalizable, or let us try to get hold of a basis consisting of eigenvectors of A. So, how are the eigenvectors of A going to behave? So, let V being equal to say x y be an eigenvector. What does that imply? This implies that A times V should be equal to 2V, right, that is how it should behave. So, i.e., so this is basically LAV, right, LAV is equal to this by definition should be equal to 2V. So, that means A is 2 1 0 2. So, this is just telling us that 2x plus y comma 2y should be equal to 2 times x comma y. That implies that 2x plus y is equal to 2x and 2y is equal to 2y. We have nothing much to say except the fact that y is equal to 0 is forced. So, if v is an eigenvector for A, then the y coordinate of v should necessarily be 0. So, that means E lambda, the eigenspace of 2 is contained in W, which is the set of all x y such that y is equal to 0. But what is the dimension of W here? Dimension of W is equal to 1, because 1 comma 0 is a basis of W. Should go back and check all these statements, and therefore, E2 being a subspace of W, which implies that dimension of E2 is less than or equal to the dimension of W, which is equal to 1. That means, dimension of E2 is equal to 1, right. So, that means, we cannot get two linearly independent vectors which has eigenvalue 2. Hence, there and 2 is the only eigenvalue, and therefore, there does not exist a basis of V consisting of eigenvectors. And therefore, T is not eigenalizable. Hence, therefore, T is not eigenalizable. So, that is quite anticlimactic if you think about it, because we were in a very nice situation where the characteristic polynomial is splitting into linear factors and still our matrix is not diagonalizable. That is quite unfortunate. So, then that prompts this next question: when can we say that even the characteristic polynomial splits, can we at all conclude that our linear operator or our matrix is diagonalizable? Can that ever be concluded? So, let us look at more examples and then let us try to see if we can say much about it. So, to do that, let us look at one more example. So, let us now work on R3 or rather 3 cross 3 matrices. So, let A now be equal to, I will just change the matrix a bit, 0 2 1 0 0 3. It is an upper triangular matrix, and the characteristic polynomial here, let me leave that to you to check, of A is f of lambda is equal to lambda minus 2 the whole square times lambda minus 3. So, there are 2 eigenvectors, or rather sorry, there are 2 eigenvalues of A. So, hence 2 and 3 are eigenvalues of A. Let us see if so we know that if we take an eigenvector corresponding to 2 and an eigenvector corresponding to 3, then we know that they are linearly independent by what we have proved. But that will only give us 2 eigenvalues, that will only give us 2 eigenvectors in a 2 linearly independent vectors in a 3-dimensional space. So, that is not enough to force it into a basis. So, let us try to get hold of eigenvectors here which are linearly independent and which are 3 of them. So, to do that, let us first focus on the eigenspace of these eigenvalues. So, consider, let V be in E2, the eigenspace of 2. Recall that eigenspace of lambda is the set of all vectors v such that T v is equal to lambda v, that was E lambda, right. So, let v be in E2. So, then what do we have? Then LAV should be equal to 2 times V, that is what it means, or in other words 200021003 times x y z, this which is equal to, so this should be equal to, I am writing to the left what it is, this is 2x 2y plus z and 3z. This should be equal to 2x 2y 2z. And what does that mean? This means that 2y plus z is equal to 2y, or z is equal to 0. The third equation also says that z is equal to 0. So, that means E2 is contained in W, or let me just put W1, which is the set of all x, y, z, such that z is equal to 0. So, let us take two vectors in W1 and see, let us take a basis of the simplest basis of W1 that we will be able to get. Let us look at 1 0 0 and 0 1 0. This is a basis of W1, and let us see what. So, let us call this V1 and let us call this V2. Let us look at what the matrix A will do to V1 and V2. So, A V1 will just turn out to be equal to x y z is sent to 2x 2y plus z. So, I will keep it like this so that it is visible. So, this is just going to 2 0 0, which is equal to 2 times 1 0 0, and hence V1 is in E2. So, similarly, what is A V2? That is also going to be x is 0, y is 1, z is 0. So, this is also going to be 0 2 0. 0 2 0, which is again 2 times 0 1 0. V2 was 0 1 0, recall that, and hence V2 also belongs to E2. How about E3? So, this is E2 for us, and how about E3? E3 is the set of all x y z such that 2x 2y plus z. So, E3 is contained in the set W2, which is the set of all x y z such that 2x is equal to 3x, 2y plus z is equal to 3y, and 3z is equal to 3z. So, this just forces y to be equal to z and x to be 0. So, this is equal to the set of all x y z such that x is equal to 0 and y is equal to z, which is the span of 0 1 1. I will leave that to you to check that this is the span of 0 1 1, and note that V3 is equal to 0 1 1 belongs to E3. Again, if beta is now equal to 1 0 0 0 1 0 and 0 1 1, this is a basis of R3 consisting of eigenvectors of A. And therefore, A is diagonalizable. So, we now have many examples of all the cases actually. We have an example when the characteristic polynomial splits, but does not have distinct eigenvalues, and when T is not diagonalizable, the one which was considered earlier, and we concluded that it cannot be diagonalized. Another example where the characteristic polynomial indeed splits, of course, but it does not split into distinct eigenvalues. It does split into distinct eigenvalues, but not n of them. So, in a 3-dimensional space which is R3, we have 2 distinct eigenvalues, but in this case it so happens that we do get a basis of R3 which consists of eigenvectors of our matrix A and hence diagonalizable. So, what changed? What changed is that here let me highlight the power of lambda minus 2, namely 2, and here again V1 and V2. Let me get hold of the two vectors V1 and V2, which is now put in green. They are linearly independent and hence a basis of the eigenspace. So, what we have is that for every eigenvalue, the multiplicity of the eigenvalue is giving us or rather we have as many number of linearly independent vectors in this case as the multiplicity of our given eigenvalues, and that is going to be the key observation to prove that or to find a condition on when our given linear operator T will be diagonalizable when the characteristic polynomial splits. So, we will be now making a few observations and proving a few theorems in order to get hold of that precise sufficient condition when we can say that our linear operator or our matrix is diagonalizable when the characteristic polynomial is given to split.